Optimizing data movement. Problems and solutions for improving performance with more data. Demand for new and better AI models is creating an insatiable demand for more processing power and much better data throughput. But it's also creating a slew of the new challenges for which there are not always good solutions. The key here is figuring out where bottlenecks might crop up in complex chips and advanced packages. This involves a clear understanding of how much bandwidth is required to move data between specific elements in a design and under specific workload, as well as a collective assessment of the throughput of that data across multiple elements, such as processors, memories, IOs, and even a lack of a service in a data center. When our customers talk about throughput and bandwidth, sometimes they talk about the whole cluster, and the whole network is acting like a compute cluster to train large AI models, observed Priyanki Shukla, Director of Product Management, Interface IP at Synopsys. What these engineering teams want to understand is throughput of a cluster and the bandwidth of a different interconnect within this cluster. They want to find the bottlenecks. There are multiple rack units in a data center. And if you open on one of the racks, you'll find one of the rack units. You'll find a processor, and through a network interface card, NIC, it connects to different racks. You have some connectivity between each SoC. Understanding how data will flow is essential to optimizing it. When a compute cluster companies train AI models, they get a lot of diagnostics information from network, and they knew precisely where the delay is, Shukla said. For example, you may have a big workload that gets thrown into this cluster, and that workload gets processed in a GPU or accelerator. Somehow, a piece of that workload has to reach a GPU, and it does that through a bunch of storage, which will be connected somewhere else in this network. From the storage, data is pulled, and through a direct memory attached DMA of a CPU, the CPU runs these algorithms or any process nearly like the first line, second line, and third line, so they can get a chunk of the data and pass it on a scale of the network to one of the accelerators, and the accelerators work together to process this data. There's a thousand of interconnects in a complex design when the data needs to be pulled from a storage. That will be over an Ethernet network that will go to a CPU and through a DMA or through a GPU in a scale-up network, Shukla noted. And all of these have the different interconnect bandwidth. If they are running over, let's just say, PCI 7.x, they are running at 128 gigabps. If they are running over Ethernet, they are running at 112 or 224 gigabps per lane. That will be the bandwidth of each of those interconnects, but the total throughput will be how the whole cluster performs. Figure 1. different architectures to solve different problems in a data center. Source: Synopsis. Status: one of the workhorses in this scenario is the serializer. The serializer. Status: technology, which compresses the parallel data into a serial data and it back again so it can move more quickly through a limited number of physical channels or pins. Data goes faster, but you don't have to do it through a large path. Said Todd Tormesolo, product marketing manager at AlphaWave Semi. You can have a minimum number of the pins that are giving you as much as you can, so it's more economically. Also, you can have a lot of more of those if you need to have the high data throughput. However, this also adds the complexity on the transmit and receive ends. The goal is to reduce this data into the smallest number of physical channels you can. Batman Solo said, at this point, that's just gonna speed up. You're gonna do a lot of tricks to compress it in there, and then it comes back. You have to reverse it. You have to take this very fast, a very physically efficient data transfer, then spread it back out to your slow and wide. Again, this process started as we started integrating compute, and it became very important physically because we cannot cable everything together the way we want. So we started out back in the 1 gigabps regime when we had something like a transmitter driving a faster receiver. When we could go pretty fast, it gave us a good parallel to serial conversion, but now we are shipping 100 gigabps, so we have to extend this similar simplistic view over the past 15 years to where we are now. We've got 200 gigabps coming next, after which is 400 gigabps, and with the application, this can't come fast enough. However, this kind of speed adds new problems. On serialized state, the transmitter, and so the serializer, the receiver, we add more complexity on the transmitter, and maybe that burns a little more power, he said. Then what we do is to look for more advanced silicon process nodes to make it smaller in order to get this extra performance, but not spend any more power while using similar wires and similar cables. On the other side, we add more processing. Maybe we want to do a simple differential compare. Maybe we have to add more gain stage. And maybe we have to add more advanced equalization, like a feed-forward equalization or a decision feedback equalizer, or some newer implemented tricks like maximum likelihood sequence detection. So, you hold this physical channel, try to make sure that people can do their 1 to 5 meter cabling, or in optical, the kilometer range. You're still trying to hold that form factor, but if you try to drive the data faster, doubling every generation, we have to put more compute and more start to help recover the signal while going at these crazy speeds. Caches. A commonly cited bottleneck is often memory, particularly in data-intensive applications such as AI training. The inability to scale SRAM quickly enough to have forced chip makers to rely on high bandwidth memory stacks on a DRAM with more data lanes in the interconnects. for L3 cache. While this is an improvement over other forms of DRAM, it's still not as fast as SRAM, which in turn created the so-called memory war. While not perfect, there are options to improve the performance of the full 3D ICs, which are not just starting to be designed. This is the typical mitigated using on-chip caches, which bring frequently used data into very fast on-chip memory that can be accessed between 10 times and 100 times faster than going to off-chip DRAM, said Rick Bai, director of the product management and marketing at Arteris. Modern SoCs may have a hierarchical cache architecture where small and very fast single-cycle access caches are embedded in the CPU core designs, often with separated caches for program and data storage, L1 caches. There also may be a larger and slightly slower second-level L2 cache that combines program and data. And in multi-core systems, perhaps a third-level L3 cache serving several CPU cores. Beyond that, there may be a last-level cache LLC or system-level cache SLC that is shared by the entire SoC, including CPU cores, GPUs, NPUs, display processors, and imaging processors connected to the cameras. That works most of the time. The sometimes data needs to be read is not available in an on-chip cache called a cache miss, which requires slow off-chip DRAM accesses. Similarly, data writes, such as camera data, may fill up the caches more quickly than they can complete background writes of data out to slower off-chip DRAM. Bai said, this bottleneck can be mitigated by increasing the number of DRAM channels. For example, instead of having only one off-chip DRAM, there can be 4, which quadruples the DRAM bandwidth, but not necessarily throughput. But this is only effective if the data can be evenly distributed across all DRAM channels with memory interleaving, which complicates system design. The standalone cache IP could be used for any cache level in the hierarchy, but especially the LRC, SLC, or a combined cache network on chip, NOC, IP can manage the need for coherency of the cached data shared by 2 or more processors to ensure the processors don't read or write stale data to cache and subsequently off-chip data that has since been updated by other processors. Multi-die integration. The disaggregations of a planar SoC into chiplets, coupled with a huge increase in the amount of data that needs to be processed with AI, has dramatically increased the focus on the data movement. You move from a paradigm where wires on chip are effectively free, and then you break it apart into multiple chips, said Kevin Donnelly, vice president of the strategy marketing of the Alien. Wires on chip are tiny, and wires that go across the package are necessarily bigger, but you can't get as many, so they are restricting the amount of data you can move between chiplets If there are two chiplets with the limited numbers of wires, you're trying to get as much bandwidth as possible between those two chiplets. If there is a standard UCIe or a bunch of wires interface where each wire is carrying data in one direction, you have a transmitter transmitting data to this chiplet and a transmitter transmitting data back to this chiplet. That's very common, and it gives you a certain amount of bandwidth per wire. But we've got a lot more data to deal with now. 4 chips used to train AI models, or those developed for high-performance computing utilization of those wires much higher than it was in the past. The tremendous explosion of bandwidth needs to be communicated between chips, and your options are either to add more wires or to try to get more bandwidth per wire, Donnelly said. To get more bandwidth per wire, you have to think about the signal integrity of the connection and in all of the signaling, where it's status or die-to-die connections. You need to look at the Nyquist rate, how fast you can learn within a given interconnection, depending on the distance and the capacitance and resistance of the interconnection. From then you can figure out how much bandwidth you can communicate over that medium. One solution is to transmit both directions at the same time on each wire, which gives twice as much bandwidth on the same number of interconnects. It's like a 2-lane highway on each road as opposed to individual split roads, Donnelly said. Ultimately, in all files, you're gonna put in parallel data, serialize it, and transmit it. Whether it's unidirectional or, in our case, simultaneous and bidirectional, it looks identical to the user. It's just more parallel wires for a given area than you'd see before. So you get better bandwidth efficiency for your silicon area, but no other difference. As soon as you disaggregated chips and you have to connect them, you have to look at the high-speed connections across them and their signal integrity, power integrity concerns, and it really is more along analog than a digital on those interconnects. Adding chiplets in a package helps overcome the limitations on processing clock speeds, but it does add more challenges when you move away from the monolithic die so that you can do chiplet-oriented design. You get the best silicon processor for your status, for your compute, and maybe for your memory, said Alphawave's Barbensoro. You don't have to use one processor for everything. You can specialize and you can use chiplet-based integration to allow you to bring it together. But you're adding in some new interfaces, and what you do the die-to-die, you're not doing the service. Rather, you do a standard like a UCIe, which adds a little bit more complexity. So even while it solves some problems, it introduces others. Intertwined challenges. It's hard enough to solve each of these issues individually, which was the classic divide and conquer approach used for SoC design. But with multi-die integration, issues need to be addressed concurrently and early in the design flow. That includes large simulations and more of them in order to map the flow of data as well as the trading of some performance for flexibility to future-proof designs. We wanna move forward in heterogeneous integration, where you can buy chiplets and integrate them just like you're buying IPs, said Vidya Neokrunda, Test Center Product Manager and Siemens CDA. As an industry, we need to work together in terms of how we can accomplish that in an IP world. You have an interface, and through that interface you can check if the IP is active and alive. After that, IP owner gives you a pattern that you can learn them. But for a chiplet, we don't have that yet. The design kits are coming into play. We need to iron out what the minimum things are that we need. It's one thing to establish the data path. It's another to ensure it'll work as expected. You may be connecting by through silicon vias, TSV, through interposer layers, EMIB, you name it. Neil Kundar said, there are so many options for connecting to them. You're not using the same path that you use for testing it in the wafer. In the wafer, you're using a Fisher probe path, but now you are using through silicon vias. It's different paths in which you're going and addressing the chiplet. Now there is a scanner fabric, which is a highway that used to send test data between the chiplet and the correct test data back from the chiplet. You can think of it as a bus, but you can do only very minimal things. You can scan out to the smaller booth, and you can use that to get the data from across the different chiplets. But industry-wide, we need a general solution. Throughput in a 2.5D and 3D IC is extremely complex. In addition to the number of elements that need to be considered, it can vary by workload, and it can be affected via various types of noise and physical effects, such as heat. When you assemble, right, the stack, you need to make sure that you are validating everything. That the signal is coming, going out, and that you are modeling it correctly. Neil Kundar said, it's a lot of pieces, especially when there might be 1 in 50 different vendors spec that you need to get going to in order to get a whole stack in play. From the fab through the TSV, the assembly could be done by somebody else. It's the same for the software and the micro inspection. Maybe you're buying the bumps from the different vendors and material from another vendor. It could be a lot of things that are in play. I believe agentic AI can act as to check the connectivity is good, allowing you to do the next step. It's not just confined to electrical signals either. In an electrical die connected over UCIe, it could as well be a photonic die, photonic integrated circuit, said Synopsis Skla. That way, from this beachfront, you can go to very large distances. We needed 200 gigabps because we wanted to go to 1 meter or 2 meter, and that's why the beachfront was higher. But now photonics provide a very beachfront efficiency manner of escape. In a UCI beachfront, you can go longer distance using photonics, and that's a new technology that will improve the beachfront density and total bandwidth and throughput correspondingly. Additionally, when trying to maximize beachfront density, there's a lot of silicon-related complexity issues that need to be accounted for. For example, if you are placing them so close to each other, the effect of the crosstalk on the multiple lanes needs to be modeled and analyzed, Shkla said. So, if an architect is just focuses on cramming in as many of these as possible, and the verification flow or the sign-up flow does involve these things, it becomes a challenging due course when the design goes for production. Dependencies and interactions all needs to be considered upfront. It's pointless to have the latest, fastest CPU cores with a large, fast cache if the interconnect does not have the throughput capacity to supply the data that the CPU needs, Artis Bai said. Traditional crossbar interconnect architectures do not scale as well. The number of the CPUs and other IP increases, and cascading smaller crossbars quickly introduces bottlenecks. The solution is to use the packetized NOC, that is, provisions with sufficient throughput to ensure that no IP is ever starved of the data it needs to get stuck, waiting to store data it has produced. Conclusion: optimizing data movement has always been a challenge, but it's becoming much more so. Whether it's a smartphone being able to access something on a data center in real time, or AI applications that are spread from one data center to another, the system is expanding and there's pieces that need to be improved. But it's being graded at a higher aggregated level, said Alpha Waves Permensoro. How do we focus on bandwidth and reach power and latency to make the very big macro scale problems better? It's no longer an individual experience. We are now relying on groups that haven't had to interact before. They need to talk, and they need to collaborate, because we no longer have a good feelings for what success is. When you have these big data center developers, they know their electricity bill. They know exactly what success is, and they can tell us what the translate to down to each one of these little SerDes interconnects, or each of these silicon chiplets. They know what they need to see, because when they scale it up by a million, over a billion, it becomes very clear to them what's critical for the next generation of development. For everyone else, putting these pieces together is gonna require a lot of more work, more standards, and more interactions with groups that traditionally have been siloed from each other. They are read this article, Optimizing Data Movement. Thank you for your time. See you next time.